Foxy was standing on the ledge of a well throwing pebbles in the water. The well is shaped like a paraboloid and it is 15 centimeters deep with a radius of 6 centimeters. Suddenly, Foxy lost balance and fell into the partially filled well. Initially, the depth of the water was 7 centimeters, but it kept filling with water. The rate at which the surface area of the well was in contact with water was 2 centimeters squared per minute. Find out how fast the water must reach 13 centimeters for Foxy to avoid drowning. For this problem, these are our given values and the things we have to find. Our main objective is to find the rate of change of the water level at 13 centimeters, dH dt. In our diagram, we can see that the total height is 15 centimeters and the total radius is 6 centimeters. We are given 13 centimeters for the height of the water and we are trying to find the radius at 13 centimeters. We can do this by using the height to radius ratio. Next, from the surface area formula, we have to derive it using a mix of product, chain, quotient, and power rules. Then we replace the variables that we know and simplify to solve for dH dt, which we solve to be this number.
Dino rushed to save Foxy when a single thread of yarn got caught in a nail. Dino tripped and he started to unravel. Dino's body continued to lose yarn until there was only his head left. Dino propelled himself forward into the air at a velocity of 0.125 centimeters per minute and going at a distance of 12 centimeters. The thread of yarn that was attached to the nail was 13 centimeters long and continued to unwind at a speed of 0.5 centimeters per minute. What was the change in rate of the volume of Dino's head as he was unraveling? In scenario 2, here are our given values. Our main objective is to find the rate at which the volume of Dino's head is decreasing. In our diagram, the distance from the nail and the length of the yarn creates a right triangle. With our given variables, we used Pythagorean theorem and solved for diameter, which was 5 centimeters. We then took the derivative of the diameter formula and solved for dr dt, which was negative 1/2 centimeters per minute. Finally, we solved for dv dt by plugging in our variables we found earlier. For our solution, we get the rate of change of the volume of Dino's head as it unravels to be negative 25 pi over 2 centimeters cubed per minute.
Hey, I don't bite. You and me, we're in a club now. What's wrong? Can't you talk?